Scientific measurement. In science, especially chemistry and physics, we have no opinion or we have no truths. We have no philosophy. We simply want to answer questions and experiment and ultimately generate numbers. And every measurement will generate a number. And the manipulation of those numbers is called reducing data, and that's what this chapter is about. It's about reducing data. The rules for reducing the data that you accumulate when you do experimentation. Chapter preview, scientific measurement, broken into 4 sections. The first section is called measurements and their uncertainty. And there are 4 subsections: using and expressing measurements, accuracy, precision, and error, significant figures in measurements, and significant figures in calculations. The second section, the International System of Units, which is a French-founded organization, and things are stored in France. We'll get to that when we get to the chapter. And it's broken into 2 subsections: measuring with SI units, that's Systems International, and units and quantities. Section 3, conversion problems. That section is broken down into 3 subsections. The first one is conversion factors, next dimensional analysis, and then the third is going to be converting between units. Section 4 is on density, and density has 2 subsections: determining density and density and temperature. Let me say something about density. Look up the lowercase Greek letter rho. That is going to be the abbreviation for density. The abbreviation for density is not D, it's rho, which looks like a P, kind of slanted to the right, a rounded letter, sort of, but it's going to be the letter rho. Objectives, section 1, measurements and their uncertainty. 3 objectives: convert measurements to scientific notation, distinguish among accuracy, precision, and error of a measurement, and the third objective, determine the number of significant figures in a measurement and in a calculated answer. The key concepts for section 1, there are 4 questions, and we'll answer the questions at the end of the chapter. How do measurements relate to science? How do you evaluate accuracy and precision? Why must measurements be reported to the correct number of significant figures? And how does the precision of a calculated answer compare to the precision of the measurements used to obtain it? There are 9 vocabulary words. I will put this same slide near the end of the chapter presentation, and we'll talk about each word. The vocabulary, the 9 words are measurement, scientific notation, accuracy, precision, accepted value, experimental value, error, percent error, and significant figures. It would be a good idea if you simply defined them, looked up their definition in various publications online, and wrote down a simple definition for each before we begin. Connecting to your world. This is a picture of a real picture of a rover that went to Mars. It's a robot that is used to collect scientific data, make measurements on a planet very far from Earth. On January 4, 2004, the Mars Exploration Rover Spirit landed on Mars, equipped with 5 scientific instruments and a rock abrasion tool, shown at left. Spirit was sent to examine the Martian surface around the Gusev crater, a wide basin that may have once held a lake. Each day of its mission, Spirit recorded measurements for analysis. This data helped scientists learn about the geology and climate on Mars. All measurements have some uncertainty. In the chemistry laboratory, you must strive for accuracy and precision in your measurements. And that's what we do. We do experiments and we accumulate data using and expressing measurements. Your height, 67 inches, your weight, 134 pounds, and the speed you drive on the highway, 65 miles per hour, are some familiar examples of measurements. A measurement is a quantity that has both a number and a unit. Everybody makes and uses measurements. For instance, you decide how to dress in the morning based on the temperature outside. If you were baking cookies, you would measure the volumes of ingredients as indicated in the recipe. Such everyday situations are similar to those faced by scientists. Now, you may use different ideas like 90 or 80 centimeters or 70 kilos, etc. So it depends on where you're from, what is familiar to you. Measurements are fundamental to the experimental sciences. For that reason, it is important to be able to make measurements and to decide whether a measurement is correct. The units typically used in the sciences are those of the International System of Measurements, SI. In chemistry, you will often encounter very large or very small numbers. A single gram of hydrogen, for example, contains approximately 602, and a lot of zeros, of hydrogen atoms. The mass of an atom of gold is very small. Writing and using such large and small numbers is very cumbersome. Here's a figure 3.1 expressing very large numbers such as estimated number of stars in the galaxy is easier if scientific notation is used. So in chemistry and physics, oftentimes we use very large numbers. You can work more easily with these numbers by writing them in scientific or exponential notation. In scientific notation, a given number is written as the product of two numbers, a coefficient and 10 raised to a power. For example, the number 602 with a lot of zeros, written in scientific notation, is 6.02 times 10 to the 23rd. The coefficient in this number is 6.02. There's only one significant figure to the left of the decimal. Please notice that. In scientific notation, the coefficient is always a number equal to or greater than 1 and less than 10. The power of 10 or exponent in this example is 23. Figure 3.1 illustrates how to express the number of stars in a galaxy by using scientific notation. For more practice on writing numbers in scientific notation, refer to page R56 of Appendix C. I will supply you with many problems to practice with for scientific notation. Accuracy, precision, and error. Your success in chemistry lab and in many of your daily activities depends on your ability to make reliable measurements. Ideally, measurements should be both correct and reproducible. Accuracy and precision. Correctness and reproducibility relate to the concepts of accuracy and precision, two words that mean the same thing to many people. In chemistry, however, their meanings are quite different. Accuracy is a measure of how close a measurement comes to the actual or true value of whatever is measured. Precision is a measure of how close a series of measurements are to one another. For instance, if the answer is 5, how close are you to 5? 4.9, 5.1, 4.8, etc. So precision usually refers to a group of numbers, a group of data. To evaluate the accuracy of a measurement, the measured value must be compared to the correct value. To evaluate the precision of a measurement, you must compare the values of two or more repeated measurements. Darts on a dartboard illustrate accuracy and precision in measurement. Let the bullseye of the dartboard represent the true or correct value of what you are measuring. The correctness of a dart to the bullseye corresponds to the degree of accuracy. The closer it comes to the bullseye, the more accurately the dart was thrown. The closeness of several darts to one another corresponds to the degree of precision. So, precision is kind of clumping the darts. The distribution of darts illustrates the difference between accuracy and precision. A, good accuracy and good precision. They're all in the bullseye. Poor accuracy and good precision is B. The darts are far from the bullseye, but close to one another. Poor accuracy and poor precision, the darts are far from the bullseye and from one another. So when you're thinking of precision, think of clumping. And when you're thinking of accuracy, think of simply the right answer. What is your goal, and have you achieved your goal? The closer together the darts are, the greater the precision and the reproducibility. Look at figure 3.2 as you consider the following outcomes. A, all of the darts land close to the bullseye and to one another. Closeness to the bullseye means that the degree of accuracy is great. Each dart in the bullseye corresponds to an accurate measurement of a value. Closeness of the darts to one another indicates high precision. All of the darts land close to one another but far from the bullseye. The precision is high because the closeness of grouping and thus the high level of reproducibility. The results are inaccurate, however, because of the distance of the darts from the bullseye. So, is it A or is it B? So when you're thinking of accuracy, again, think of the right answer. And when you're thinking of precision, think of clumping. Striving for scientific accuracy. The French chemist Antoine Lavoisier worked hard to establish the importance of accurate measurement in scientific inquiry. Lavoisier devised an experiment to test the Greek scientists' idea that when water was heated, it turned it into earth. For 100 days, Lavoisier boiled water in a glass flask constructed to allow steam to condense without escaping. He weighed the water and the flask separately before and after boiling. He found that the mass of the water had not changed. The flask, however, lost a small mass equal to the sediment he found in the bottom of it. Lavoisier proved that the sediment was not earth, but part of the flask etched away by the boiling water. C. The darts land far from one another and from the bullseye. The results are both inaccurate and imprecise. Now, determining error. Note that an individual measurement may be inaccurate or accurate. Suppose you use a thermometer to measure the boiling point of pure water at standard pressure. The thermometer reads 99.1 degrees Celsius. You probably know that the true or accepted value of the boiling point of pure water under these conditions is actually 100 degrees Celsius. There is a difference between the accepted value, which is the correct value based on reliable references, and the experimental value, the value measured in the lab. That's the experimental value. The difference between the experimental value and the accepted value is called the error. Error equals experimental value minus accepted value. Error can be positive or negative depending on whether the experimental value is greater than or less than the accepted value. For the boiling point measurement, the error is negative 0.9 degrees Celsius. The magnitude of the error shows the amount by which the experimental value differs from the accepted value. Often it is useful to calculate the relative error, or percent error. It will become obvious to you that the error is an absolute quantity, meaning it has no direction, it has no sign, it's just a natural number. It's called an absolute value, so it's going to be 0.9 degrees Celsius. The percent error is the absolute value of the error divided by the accepted value, multiplied by 100%. Using the absolute value of the error means that the percent error will always be a positive value. That's not completely true, but all right, fair enough. For the boiling point measurement, the percent error is calculated as follows. Follow along with the calculations on the next page. Here I have the equation for percent error, relative error, and follow the calculations along. It's actually very simple, and the answer is 0.9% error, which relative to a thermometer is fairly high, especially if you're finding the boiling point of water. The scale above has not been properly zeroed. This is figure 3.3. So the reading obtained for the person's weight is inaccurate. There is a difference between the person's correct weight and the measured value. Calculating what is the percent error of the measured value of 114 pounds if the person's actual weight is 107 pounds. So when you make measurements, you have to make sure that everything is zeroed. Very important. Just because a measuring device works doesn't necessarily mean that it is accurate. As figure 3.3 shows, a weighing scale that does not read zero when nothing is on it is bound to yield error. In order to weigh yourself accurately, you must first make sure that the scale is zero. This kind of error is called systematic error, systems error, meaning there was something wrong with either the experimental instruments or the procedure that was written down. Figure 3.3, precision of a weighing scale depends on how finely it is calibrated. This is a produce scale, and Hobart is a very big name in the United States. I don't know where they're made, but it's a very common company. Significant figures in measurements. Supermarkets often provide scales like the one in figure 3.4. Customers use these scales to make the weight of produce that is price per pound. If you use a scale that is calibrated in 0.1 pound intervals, you can easily read the scale to the nearest tenth of a pound. With such a scale, however, you can also estimate the weight of the nearest hundredth of a pound by noting that the position of the pointer between the calibration marks. Suppose you estimate a weight that lies between 2.4 pounds and 2.5 pounds to be 2.46 pounds. The number in the estimated measurement has three significant figures. The first two digits in the measurements, 2 and 4, are known with certainty. Three different calibrated meter sticks are used to measure the length of a board. A meter stick calibrated in a 1 meter interval. B, a meter stick calibrated in a 0.1 meter interval. And C, a meter stick calibrated in a 0.01 meter intervals. Measuring how many significant figures are reported in each measurement. And you can see that the measurements are done for you and the number of significant figures are clearly listed. 0.6 has 1, 0.61 has 2, etc. But the rightmost digit in 6, the 6, has been estimated and involves some uncertainty. These three reported digits all convey useful information, however, and are called significant figures. The significant figures in a measurement include all of the digits that are known, plus a last digit that is estimated. Measurements must always be reported to the correct number of significant figures because calculated answers often depend on the number of significant figures in the values used in the calculation. Instruments differ in the number of significant figures that can be obtained from their use and thus in the precision of measurements. The 3 meter sticks in figure 3.5 can be used to make successfully more precise measurements on the board. Rules for determining whether a digit is measured, the measured value is significant. All right, so we're going to decide on if we didn't actually do the measurement and we're given a measurement, how do we determine how many significant figures are in the measurement? There are 4 rules. If you're actually accumulating the data in the lab, you can tell the significant figures, and we'll go through that when we do lab work. But what happens if you're given data? How do you know what's significant and what isn't significant? So let's read this very carefully. We'll start with number 1. So number 1 says every non-zero digit in a reported measurement is assumed to be significant. The measurement's 24.7 meters, 0.743 meters, and 714 meters. Each are express a measure of length to 3 significant figures. Now you see the measurement 0.743. That 0 is just a formatting number. It's a long story. I don't want to get into it right now, but it means nothing. You don't even have to put it. It means absolutely nothing. It doesn't do anything. So you have 3 significant figures in each one of those measurements. Number 2, zeros appearing between non-zero digits are significant. The measurement 7003 meters, 40.79 meters, and 1.503 meters each have 4 significant figures. I'm going to extend this rule just a little bit. You see where it says zeros appearing between non-digits are significant? Well, any 0 between 2 significant figures are significant. For instance, a 0 can be significant. So if a 0 is on the end, then it's going to be significant. And any zeros between 2 significant digits are significant. And I'll make this a little clearer in the next couple of rules. Leftmost zeros appearing in front of non-zero digits are not significant. They act as placeholders. The measurement 0.0071 meters, the 2 zeros before the 7, 0.42, the 0.42, that's really nothing, and 0.000099 meters, each only have 2 significant figures. The zeros to the left are not significant. The zeros to the left are not significant. By writing the measurements in scientific notation, you can eliminate such placeholders or placeholding zeros in case 7.1 times 10 to the negative third meters, 4.2 times 10 to the negative 1 meters, and 9.9 times 10 to the negative 5 meters. You see, in scientific notation, you only use significant figures, so there's no worries about what's significant and what isn't significant. However, if you're going to convert to scientific notation, you have to know which digits are significant to put in the scientific notation, or you'll be wrong. Number 4, zeros at the end of a number and to the right of a decimal point are always significant. It's a little weird. All right, this is a hard one. The measurement's 43.00, 1.010, and 9.000 meters. Each have 4 significant figures. So, look at the third one, 9.000. Now, look at it this way. It's the last 0 to the right of the decimal that is significant. Got it? So the last digit to the right of the decimal. So you have the 9, so the fourth digit to the right. That 0 is significant. Yes, you get that. It's to the right of the decimal. It's a 0. It's significant. Okay, now you know that you understand that the 9 is significant because that's a non-zero digit. That's always significant. Okay, so that last digit, that last 0 is significant. The 9 is significant. So now let's look back at that rule that says any zeros between two significant figures, between two non-zero numbers. And I said between two significant figures, and that's where the rule comes in. So the 9 is significant, the last 0 on the right is significant, and everything in between is significant because the rule should say any zeros between two significant figures are significant. So that's why you have 4 significant figures, especially for the 9.000. That third 0, the 0 to the right, is significant. Let me just say one thing before we continue, and that is that these look a little weird. Don't worry about it. The practice, it will become very familiar to you. So don't worry about it. It sounds like a bunch of gobbledygook, but you've got to simply practice. It's a skill, so you'll figure it out. Now, number 5, zeros at the rightmost end of a measurement that lie to the left of an understood decimal point are not significant if they serve as placeholders to show the magnitude of a number. The zeros in the measurement 300 meters, 7000 meters, and 27210 meters are not significant. The numbers of significant figures in these values are 1, 1, and 4, respectively. If such zeros were known measured values, however, then they would be significant. For example, if all of the zeros in the measurement, 300, were significant, writing the value in scientific notation as 3.00 times 10 to the 2 meters makes it clear that these zeros are significant. Number 6, there are 2 situations in which numbers have an unlimited number of significant figures. Now, this is important. It's actually very easy. The first involves counting. If you count 23 people in your classroom, then there are exactly 23 people. And this value has an unlimited number of significant figures. The second situation involves exactly defined quantities, such as those found within a system measurement. When, for example, you write 60 minutes equals 1 hour, or 100 centimeters equals 1 meter. Each of these numbers has an unlimited number of significant figures. As you shall soon see, exact quantities do not affect the process of rounding an answer to the correct number of significant figures. And I'm going to tell you why. Those are conversions. The second example was conversions. Conversions aren't measurements. Conversions are conversions. When you multiply, divide, add, or subtract measurements, that's when you're going to apply certain rules. So it's not to worry. And I will give you in class, I will give you 2 more simple rules that will make everything come together a little bit more clearly. Okay? All right. Enough said. Significant figures in calculation. Suppose you use a calculator to find the area of a floor that measures 7.7 meters by 5.4 meters. The calculator would give you an answer of 41.58 square meters. The calculated area is expressed to 4 significant figures. However, each of the measurements used in the calculation is expressed to only 2 significant figures. So the answer must also be reported to 2 significant figures, 42 meters squared. In general, a calculated answer cannot be more precise or more accurate than the least precise measurement from which it was calculated. The calculated value must be rounded to make it consistent with the measurements from which it was calculated. That's worded very poorly, but I'll make things a little bit more clear in class, but it's okay, it's not bad. Rounding. To round a number, you must first decide how many significant figures the answer should have. This decision depends on the given measurements and on the mathematical process used to arrive at the answer. Once you know the number of significant figures your answer should have, round to that many digits, counting from the left. If the digit immediately to the right of the last significant digit is less than 5, it simply dropped, and the value of the last significant digit stays the same. It's called rounding down, but you're really not rounding down. If the digit in question is 5 or greater, the value of the digit in the last significant place is increased by 1. Why must the calculated answer generally be rounded? That's your question. Addition and subtraction. The answer to an addition or subtraction calculation should be rounded to the same number of decimal places, not digits, as the measurement with the least number of decimal places. Working through sample problem 3.2 below, which provides an example of rounding in an addition calculation. And I will do another PowerPoint to show you some of these rules. But let's reword this rule just a little bit. Your answer in an addition or subtraction must have the same precision as the measurement with the least precision. And the answer to the question, why round? Because your answer must have the same accuracy as the least accurate value and the same precision as the least precise value, and you achieve that by rounding. Multiplication and division. In calculations involving multiplication and division, you need to round the answer to the same number of significant figures as the measurement with the least number of significant figures. The position of the decimal point has nothing to do with the rounding process when multiplying and dividing measurements. The position of the decimal point is important only in rounding the answers of addition or subtraction problems. Checkpoint. How many significant figures must you round an answer to when performing a multiplication or division? Multiplication and division is a function of accuracy, and the number of significant figures is a function of accuracy. The more number of significant figures you have, the more the accuracy. The fewer number of significant figures you have, the less the accuracy. When multiplying and dividing, your answer must have the same accuracy as the least accurate value, so the fewest number of significant figures. Section 2, the International System of Units. List SI units of measurements and common SI prefixes. Distinguish between the mass and weight of an object. Convert between the Celsius and Kelvin temperature scales. Section 2, key concepts, the International System of Units. Which 5 SI base units do chemists commonly use? What metric units are commonly used to measure length, volume, mass, temperature, and energy? Vocabulary, International System of Units, SI, meter, liter, kilogram, gram, weight, temperature, Celsius scale, Kelvin scale, absolute zero, energy, it's pronounced joule, it's the last name of a person, and calorie. Connecting to your world. Here are some street signs, and they are from England, the Midlands area, I would presume, somewhere. Are we there yet? You may have asked this question during a long road trip with family or friends. To find out how much farther you have to go, you can read the roadside signs that list destinations and their distances. In the signs shown here, however, the distances are listed as numbers with no units attached. Is carried in 44 kilometers or 44 miles. Without the units, you can't be sure. When you make a measurement, you must assign the correct units to the numerical value. Without the units, it is impossible to communicate the measurement clearly to others. If you weigh 50 kilos, you've got to put kilograms. If you put meters, that makes no sense. I weigh 50 meters. It makes no sense. So you got to make sure the units are correct. Measuring with SI units. All measurements depend on units that serve as reference standards. The standards of measurement used in science are those of the metric system. The metric system is important because of its simplicity and ease of use. All metric units are based on multiples of 10. As a result, you can convert between units easily. The metric system was originally established in France in 1795. The International System of Units, abbreviated SI after the French name, Le Système International de Units, I have no idea how to pronounce that, is a revised version of the metric system. The SI was adopted by the International Agreement in 1960. So the metric system as we know it is actually a subset of the SI. Here is table 3.1, SI base units. In other words, we use meter, we use length. Mass is kilograms, even though we use grams. It's kilograms, Kelvin. So these are the standards that are used. There are 7 SI base units, which are listed in table 3.1. From these base units, all other SI units of measurement can be derived. The 5 SI base units commonly used by chemists are the meter, the kilogram, the Kelvin, the second, and the mole. All measured quantities can be reported in SI units. Sometimes, however, non-SI units are preferred for convenience or for practical reasons. In this textbook, you will learn about both SI and non-SI units. For instance, we use milliliter a lot. We use gram a lot. Units and quantities. As you already know, you don't measure length in kilograms or mass in centimeters. Different quantities require different units. Before you make a measurement, you must be familiar with the measurement, with the units corresponding to the quantity that you are trying to measure. Units of length. Size is an important property of matter. In SI, the basic unit of length or linear measure is the meter, M. All measurements of length can be expressed in meters. The length of a page in this book is about 1/4 of a meter, or 25 centimeters. So, meter. We'll use centimeters a lot. We'll use a variety of things. Here are commonly used metric prefixes. Study these carefully. You must know them, they are required. Here are some metric units of length. You must know these, study these carefully. Very important and very useful. And the examples are most excellent. For very large and very small lengths, however, it may be more convenient to use a unit of length that has a prefix. Table 3.2 lists the prefixes in common use. For example, the prefix milli means 1,000th. So a millimeter is 1,000th of a meter, or 0.001 meters. A hyphen measures about 1 millimeter. Well, that hyphen's a little bit more than a millimeter. For large distances, it is usually most appropriate to express measurements in kilometers. The prefix kilo means 1,000. So 1 km means 1,000 meters. A standard marathon distance race is about 42,000 meters. is more conveniently expressed as 42 kilometers, or 42 times 1,000 meters. Common metric units of length include centimeter, meter, and kilometer. Table 3.3 summarizes the relationships among metric units of length. These photographs above give you some idea of the relative sizes of some different units of volume. A, the volume of 20 drops of liquid from a medicine dropper is approximately 1 milliliter. A sugar cube is about 1 centimeter on each edge and has a volume of 1 cubic centimeters. Note that 1 milliliter is the same as 1 cubic centimeter. C, a gallon of milk has about twice the volume of a 2-liter bottle of soda, calculating how many cubic centimeters are in 2 liters. Units of volume. The space occupied by any sample of matter is called its volume. You calculate the volume of any cubic or rectangular solid by multiplying its length by its width by its height. The unit for volume is thus derived from units of length. The SI unit of volume is the amount of space occupied by a cube that is 1 meter along each side. This volume is a cubic meter, m to the third. An automatic dishwasher has a volume of about a cubic meter. A more convenient unit of volume for everyday use is the liter, a non-SI unit. A liter is the volume of a cube that is 10 centimeters along each edge. 10 centimeters times 10 centimeters, etc., equals 1,000 cubic centimeters equals 1 liter. SI units of distance and time. In 1790, with the establishment of the metric system, the French became the first to adopt measurement standards that were close to being precise. The meter was defined as 1/10,000,000th of the distance from the equator to the North Pole along the meridian that passes through Paris. The second was defined as 1/86,400 of the average day. The definition of these and other base units have since become more precise. The meter is now defined as the distance traveled by light in a vacuum in 1/299,792,458 of a second. The second is now defined in terms of the number of cycles of radiation given off by a specific isotope of the element cesium. Table 3.4, metric units of volume. These are some commonly used relationships of units for volume that we may use in a chemistry laboratory. I have used all of them in a chemistry laboratory. A decimeter is equal to 10 centimeters. So 1 liter is also equal to 1 cubic decimeter. A smaller non-SI unit of volume is the milliliter, M capital L. We usually use M small l, same. 1 milliliter is 1,000th of a liter. Thus, there are 1,000 milliliters in a liter because 1 liter is defined as 1,000 cubic centimeters. 1 milliliter equals 1 cubic centimeter are the same volume. The units milliliter and cubic centimeter are thus used interchangeably. Common metric units of volume include the liter, milliliter, cubic centimeter, and microliter. Table 3.4 summarizes the relationships among these units of volume. There are many devices for measuring liquid volumes, including graduated cylinders, pipettes, burettes, volumetric flasks, and syringes. Note that the volume of any solid, liquid, or gas will change with the temperature, although the change is much more dramatic for gases. Consequently, accurate volume measuring devices are calibrated at a given temperature, usually 20 degrees Celsius, which is about normal room temperature. What is the SI unit of volume? Metric units of mass: kilogram, gram, milligram, microgram. Study these. You have examples which are most excellent. And there you have it. Units of mass. The mass of an object is measured in comparison to a standard mass of 1 kilogram, which is the basic SI unit of mass. A kilogram was originally defined as the mass of 1 liter of liquid water at 4 degrees Celsius. A cube of water at 4 degrees Celsius measuring 1 centimeter on each side would have a volume of 1 liter and a mass of 1,000 grams or 1 kilogram. A gram is 1,000th of a kilogram. The mass of 1 cubic centimeter of water at 4 degrees Celsius is 1 gram. Common metric units of mass include the kilogram, gram, milligram, and microgram. The relationships among units of mass are shown in Table 3.5. You can use a platform balance to measure the mass of an object. An astronaut's weight on the moon is 1/6 as much as it is on Earth. Earth exerts 6 times the force of gravity as the moon, inferring. How does the astronaut's mass on the moon compare to his mass on Earth? The object is placed on one side of the balance, and a standard mass is added to the other side until the balance beam is level. The unknown mass is equal to the sum of the standard masses. Laboratory balances range from very sensitive, ultra-sensitive instruments with a maximum capacity of only a few milligrams to devices for measuring quantities in kilograms. An analytic balance is used to measure objects of less than 100 grams and can determine mass to the nearest 0.0001 or 0.1 milligram. The astronaut shown on the surface of the moon in figure 3.7 weighs 1/6 of what he weighs on Earth. The reason for this difference is that the force of gravity on Earth is about 6 times what it is on the moon. Weight is a force that measures the pull on a given mass by gravity. Weight, a measure of force, is different from mass, which is a measure of the quantity of matter. Although the weight of an object can change with its location, its mass remains constant regardless of its location. Objects can become weightless, but they can never become massless. Checkpoint. How does weight differ from mass? Well, first of all, on the moon, let's say they weigh 60 kilograms on Earth. They only weigh 10 kilograms on the moon. That's the first thing. And the difference between weight and mass is that weight is subject to gravity, mass is not. When we study physics next year, or when you study physics next year, it has to do with inertia, but I'll explain that during class. Thermometers are used to measure temperature. A liquid in glass thermometer contains alcohol or mineral spirits. A dial thermometer contains a coiled bimetallic strip. A Galileo thermometer contains several glass bulbs that are calibrated to sink or float depending on the temperature. This Galileo thermometer shown uses the Fahrenheit scale, which sets the freezing point of water at 32 degrees Fahrenheit and the boiling point of water at 212 degrees Fahrenheit. Units of temperature. When you hold a glass of hot water, the glass feels hot because heat transfers from the glass to your hand. When you hold an ice cube, it feels cold because heat transfers from your hand to the ice cube. Temperature is a measure of how hot or cold an object is. An object's temperature depends on the direction of the heat transfer. When two objects at different temperatures are in contact, heat moves from one object at the higher temperature to the object at the lower temperature. Almost all substances expand with an increase in temperature and contract as temperature decreases. A very important exception is water, which expands between 4 and 0 degrees Celsius. These properties are the basis for the common liquid in glass thermometer. The liquid in the thermometer expands and contracts more than the volume of the glass, producing changes in the column height or of the liquid. Figure 3.8 shows a few different types of thermometers. Several temperature scales with different units have been devised. Scientists commonly use two equivalent units of temperature, the degree Celsius and the Kelvin. The Celsius scale of the metric system is named after the Swedish astronomer Anders Celsius, 1701 to 1744. It uses two readily determined temperatures as reference temperatures values, the freezing point and boiling point of water. These thermometers show a comparison of the Celsius and Kelvin temperature scales. Note that 1 degree Celsius change on the Celsius scale is equal to 1 K change on the Kelvin scale. Interpret diagrams. What is a change in 10 Kelvin, 10 K, equivalent to on the Celsius scale? 10 degrees Celsius. The Celsius scale sets the freezing point of water at 0 degrees Celsius and the boiling point of water at 100 degrees Celsius. The distance between these two fixed points is divided into 100 equal intervals, or degrees Celsius. Another temperature scale used in the physical sciences is the Kelvin, or absolute scale. This scale is named for Lord Kelvin, 1824 to 1907, a Scottish physicist and mathematician. On the Kelvin scale, the freezing point of water is 273.15 kelvins, and the boiling point is 373.15 Kelvin. Notice that with the Kelvin scale, the degree sign is not used. Figure 3.9 on the next page compares the Celsius and Kelvin scales. A change of 1 degree on the Celsius scale is equivalent to 1 Kelvin on the Kelvin scale. Look back at figure 3.9 and make sure that makes sense to you. The 0 point on the Kelvin scale, 0K, is absolute zero, is equal to negative 273.15 degrees Celsius. For problems in this text, you can round negative 273.15 degrees Celsius to negative 273 degrees Celsius, because 1 degree on the Celsius scale is equivalent to 1 Kelvin on the Kelvin scale. Converting from one temperature to another is easy. You simply add or subtract 273 as shown in the following equation. Study those equations carefully. Photoelectric panels convert solar energy into electricity. What did Albert Einstein win the Nobel Prize for? First person tells me gets extra credit. Units of energy. Figure 310 shows a house equipped with solar panels. The solar panels convert the radiant energy from the sun into electrical energy that can be used to heat water and power appliances. Energy is the capacity to do work or to produce heat. Like any other quantity, energy can be measured. The joule and the calorie are common units of energy. The joule, capital J, is the SI unit for energy. It is named after the English physicist James Prescott Joule, 1818 to 1889. 1 calorie is the quantity of heat that raises the temperature of 1 gram of pure water 1 degree Celsius. Conversions between joules and calories can be carried out using the following relationships. Study those carefully. Near absolute zero temperature. The coldest temperature achieved so far in a laboratory is 1/2 nanokelvin. That is that large, very small number, above absolute zero. Compare this temperature to the cold temperature of outer space, which is about 2.7 Kelvin. That's an average, so it could be very near 0 degrees Kelvin. That's a misleading value. It's that's of the universe is about 2.7 K, but that includes everything. Construct conversion factors from equivalent measurements. Apply the technique of dimensional analysis to a variety of conversion problems. Solve problems by breaking the solution into steps. Convert complex units using dimensional analysis. Section 3, conversion problems. These are the key concepts. Questions. What happens when a measurement is multiplied by a conversion factor? Why is dimensional analysis useful? What types of problems are easily solved by using dimensional analysis? Vocabulary, conversion factor, and dimensional analysis. Connecting to your world. Here are various currencies, both paper and metal, from around the world. Perhaps you have traveled abroad and are planning to do so. If you know or will soon discover that different countries have different currencies, as a tourist, exchanging money is essential to the enjoyment of your trip. After all, you must pay for your meals, hotel, transportation, gift purchases, and tickets to exhibits and events. Because each country's currency compares differently with the United States dollar, knowing how to convert currency units correctly is very important. Conversion problems are readily solved by a problem-solving approach called dimensional analysis. Conversion factors. If you think about any number of everyday situations, you will realize that a quantity can usually be expressed in several different ways. For example, consider the monetary amount $1. $1 equals 4 quarters, equals 10 dimes, equals 20 nickels, equals 100 pennies. These are all expressions or measurements of the same amount of money. The same thing is true of scientific quantities. For example, consider a distance that measures exactly 1 meter. 1 meter equals 10 decimeters equals 100 centimeters equals 1,000 millimeters. These are different ways to express the same length. Whenever two measurements are equivalent, a ratio of the two measurements will equal 1, or unity, or a factor of 1. For example, you can divide both sides of the equation, as is shown here. 1 meter over 1 meter is 1, 100 centimeters over 1 meter is 1, etc. Conversion factors is the ratio of equivalent measurements. Numerator and denominator are equivalent. The ratios 100 centimeters over 1 meter and 1 meter over 100 centimeters are examples of conversion factors. Two parts of a conversion factor, the numerator and the denominator, are equal. Or you should say, more correctly, they are equivalent. 1 meter is equivalent to 100 centimeters. That's a better mathematical way of putting it. In a conversion factor, the measurement in the numerator on the top is equivalent to the measurement in the denominator or on the bottom. The conversion factor above is read 100 centimeters per meter and 1 meter per 100 centimeters. Figure 3.11 illustrates another way to look at the relationships in a conversion factor. Notice that the smaller number is part of the measurement with the larger unit. That is, a meter is physically larger than a centimeter. The larger number is part of the measurement. with the smallest unit conversion factors are useful in solving problems in which a given measurement must be expressed in some other unit of measure. When a measurement is multiplied by a conversion factor, the numerical value is generally changed, but the actual size of the quantity measured remains the same. For example, even though the numbers in the measurements 1 gram and 10 decigrams differ, both measurements represent the same mass. In addition, conversion factors within a system of measurement are defined quantities or exact quantities. Therefore, they have an unlimited number of significant figures and do not affect the rounding of the calculated answer. Here are some additional examples of pairs of conversion factors written from equivalent measurements. The relationship between grams and kilograms is 1,000 grams, equals 1 kilogram. So as long as they're equal, they are equivalent. In this computer image of atoms, this is a tunneling microscope actually, distance is marked off in nanometers. It's the one on the left. Inferring what conversion factor would you use to convert nanometers to meters? Well, a nanometer is a billionth of a meter, so it would be 10 to the ninth. So 10 to the ninth nanometers equals 1 meter. That would be a convenient conversion factor. Now it's the one on the left. The one on the right I took from the internet. These are images from what they call a tunneling microscope, and they are images of atoms, believe it or not. Unbelievable. The conversion factors are 1,000 grams over 1 kilogram and 1 kilogram over 1,000 grams. The scale of the micrograph in figure 3.12 is in nanometers, using the relationship 10 to the ninth nanometers equals 1 meter. You can write the following conversion factors: 10 to the ninth nanometers over 1 meter, and 1 meter over 10 to the ninth nanometers. Common volumetric units used in chemistry include the liter, the microliter. The relationship 1 liter equals 10 to the sixth microliters. Micro is millionth, 10 to the negative sixth. So there's a million microliters in a liter, yields the following conversion factors: 1 liter over 10 to the sixth microliters, and 10 to the sixth microliters over 1 liter. Based on what you know about metric prefixes, you should be able to easily write conversion factors that relate equivalent metric quantities. Checkpoint. How many significant figures does a conversion factor within a system of measurement have? Unlimited. It's really quite irrelevant in terms of identifying the number of significant figures after multiplication and division, but it's unlimited if it's within a system. Dimensional analysis. No single method is best for solving every type of problem. Several good approaches are available, and generally one of the best is dimensional analysis. Dimensional analysis is a way to analyze and solve problems using the units or dimensions of the measurements. The best way to explain this problem-solving technique is to use it to solve an everyday situation. There is usually more than one way to solve a problem. When you first read sample problem 3.5, you may have thought about different and equally correct ways to approach and solve the problem. In physics, it's a little different. Chemistry and physics utilizes dimensional analysis in a bit differently. So be ready in physics to look at dimensional analysis a little bit differently, but I will explain more during class. Monetary exchange rates. The conversion of chemical units is similar to the exchange of currency. Americans who travel outside the United States must exchange US dollars for foreign currency at a given rate of exchange. These exchange rates vary from day to day. The daily exchange rates affect all international monetary transactions. Each time one type of money is exchanged for another, The current exchange rate serves as a conversion factor. International currency traders keep track of exchange rates 24 hours a day through a linked computer network. Some problems are easily worked with simple algebra. Dimensional analysis provides you with an alternative approach to problem solving. In either case, you should choose the problem solving method that works best. Converting between units. In chemistry, as in many other subjects, you often need to express a measurement in a unit different from the one given or measured initially. Problems in which a measurement with one unit is converted to an equivalent measurement with another unit are easily solved using dimensional analysis. Suppose that a laboratory experiment requires 7.5 decigrams of magnesium metal, and 100 students will do the experiment. How many grams of magnesium should your teacher have on hand? Multiply 100 students by 75 decigrams per student, gives you 750 decigrams. But then you must convert decigrams to grams. Sample problem 3.7 shows you how to do the conversion. Multi-step problems. Many complex tasks in everyday life are best handled by breaking them down into manageable parts. For example, if you were cleaning a car, you might first vacuum the inside, then wash the exterior, then dry the exterior, and finally put a fresh coat of wax. Similarly, many complex word problems are more easily solved by breaking the solution down into steps. When converting between units, it is often necessary to use more than one conversion factor. Sample problem 3.8 illustrates the use of multiple conversion factors. Checkpoint. When problem-solving methods can help you solve complex word problems, or what problem-solving methods can help you solve complex word problems? We will answer that question in class. Converting complex units. Many common measurements are expressed as ratio of two units. For example, the results of international car races often give average lap speed in kilometers per hour. You measure the densities of the solids of liquids in grams per cubic centimeter. You measure the gas mileage in a car in miles per gallon of gasoline. If you use dimensional analysis, converting these complex units is just as easy as converting single units. It will just take multiple steps to arrive at an answer. This is mercury. It's a liquid metal. It has a very high density, even though it's a liquid at room temperature. It's a very shiny, metallic, silvery color. Density, section 4. Calculate the density of a material from experimental data. Describe how density varies with temperature. Key concepts, density, section 4. What determines the density of a substance? How does a change in temperature affect density? Vocabulary, the only word listed is density. And next to the word density, I have a rho, the Greek letter lowercase rho, which stands for density. The lowercase rho stands for density. Connecting to your world, here are some water lilies that float on the water. Have you ever wondered why some objects float in water while others sink? If you think that these lily pads float because they are lightweight, you are only partially correct. The ratio of the mass of the object to the volume can be determined to determine whether an object floats or sinks in water. For pure water, 4 degrees Celsius, the ratio is 1 gram per cubic centimeter. If an object has a mass to volume ratio of less than 1, it will float in water. If an object has a mass to volume ratio greater than this value, it will sink in water. Determining density. Perhaps someone has tricked you with the question, which is heavier, a pound of lead or a pound of feathers? Most people would not give the question much thought and would incorrectly answer lead. Of course, 1 pound of lead has the same mass as a pound of feathers. What concept instead of mass are people really thinking of when they answer this question? Most people are incorrectly applying a perfectly correct idea, namely that if a piece of lead and a feather of the same volume or weight, the lead would have a greater mass than the feather. It would take a much larger volume of feathers to equal the mass of a given volume of lead. The important relationship in this case is between the object's mass and its volume. This relationship is called density. Density is the ratio of the mass of an object to its volume. Density equals mass over volume. A 10 cubic centimeter piece of lead, for example, has a mass of 114 grams. What then is the density of lead? You can calculate it by substituting the mass and volume into the equation. Density equals 114 divided by 10 equals 11.4 grams per cubic centimeter. A 10-gram sample of pure water has less volume than 10 grams of lithium, but more volume than 10 grams of lead. The faces of the cubes are shown actual size, inferring which substance has the highest ratio of mass to volume. Table 3.6, some densities of common materials. Here are some common materials listed, and what I do is I split the table in half. Here is a iron floating on mercury, and this is between the two tables that I cut in half. The iron nut that goes on a bolt is floating on liquid mercury because of the difference in density. Here are some additional densities of materials. Solids and liquids on the left and gases on the right. Note that when mass is measured in grams, the volume is cubic centimeters. Density has units of grams per cubic centimeter. Figure 3.13 on page 89 compares the density of three substances. Why does each 10-gram sample have a different volume? The volumes vary because the substance has different densities. Density is an intensive property that depends only on the composition of the substance, not on the size of the sample, as long as the temperature is constant. With a mixture, densities can vary because the composition of the mixture can vary. What do you think will happen if corn oil is poured into a glass containing corn syrup? Using table 3.6, you can see that the density of corn oil is less than the density of corn syrup. Figure 3.14, because of differences in density, corn oil floats on top of corn syrup. For that reason, the oil floats on top of the syrup, as shown in figure 3.14. You have probably seen a helium-filled balloon rapidly rise to the ceiling when it is released. Whether a gas-filled balloon will sink or rise when released depends on how dense, or depends on the density of the gas compared with the density of air. Helium is less dense than air, so the helium-filled balloon rises. The densities of various gases are shown in table 3.6. What quantities do you need to measure in order to calculate the density of an object? Mass and volume. Density and temperature. Experiments show that the volume of most substances increase as the temperature increases. Meanwhile, the mass remains the same despite the temperature and volume changes. Remember that density is the ratio of an object's mass to its volume. So, if the volume changes with temperature, while the mass remains constant, then the density must also change with temperature. The density of a substance generally decreases as its temperature increases. As you will learn in chapter 15, water is an important exception. Over a certain range of temperatures, 0 to 4 degrees Celsius, the volume of water increases as its temperature decreases. Ice or solid water floats because it is less dense than liquid water. Specific gravity. Specific gravity is the ratio of the density of a substance to the density of a reference substance, usually at the same temperature. Water at 4 degrees is often the reference substance. Physicians use the measured specific gravity of a patient's urine to help diagnose certain diseases such as diabetes. Auto mechanics measure the specific gravity of antifreeze in radiator during tune-ups. Key ideas, section 1, measurements and their uncertainty. Measurements are fundamental to the experimental sciences. To evaluate accuracy, the measured value must be compared to the correct value. To evaluate precision, you must compare the values of repeated measurements. Calculated answers often depend on the number of significant figures in the values used in the calculation. In general, a calculated answer cannot be more precise than the least precise measurement from which it is calculated. Section 2, the International System of Units. 5 commonly used SI-based units are the meter, the kilogram, the Kelvin, second, and mole. Common metric unit of length, centimeters, meters, kilometers. Common metric units of volume, microliters, milliliters, liters, and cubic centimeters. Common metric units of mass, milligrams, grams, kilograms. Common units of temperature, degrees Celsius, and Kelvin. Common units of energy, joules, and calories. Conversion problems. Multiplied by a conversion factor does not change the actual size of a measurement. Dimensional analysis provides an alternate approach to problem solving. Conversion problems are easily solved using dimensional analysis. Density. Density is an intensive property that depends only on the composition of a substance. The density of a substance generally decreases as its temperature increases. I decided not to put the slides of vocabulary at the back of this lecture. I want you to define those words in the vocabulary as part of the chapter outline. We will discuss more about the chapter outline in class, and I will make a separate presentation on what the chapter outline is going to be used for and how to do the chapter outline.